Hey, I'm going to try to go through as much of the practice exam as possible, and that way I can hopefully answer any questions that you still had after working through it. The first question is asking about the nomenclature of ionic compounds, and it focuses on lithium atoms and sulfur atoms. So it's asking you to form a neutral salt. Remember that neutral means that you have a net charge of 0. And so, okay, you have one sulfur, and it's asking you how many lithiums you will need to balance this charge out. Sulfur is in group 6, right underneath oxygen, and so its charge is -2, because it'll gain 2 electrons to satisfy the octet, and in doing so, it had a charge of 0 first, but then because it gained 2 electrons, which are negatively charged, its overall charge became -2. So lithium, if you look for lithium in the periodic table, it's in group 1, so it's going to have a charge of +1. And you're basically trying to figure out how many of these you need in order to cancel out the -2 charge. So if this one has a +1, you're going to need another lithium that's going to bring in another +1 to cancel out the -2. And then you'll have -2 on this side, +2 on this side, which will give you 0. So you'll need 2 lithium atoms in order to create a neutral salt. For question number 2, it says nomenclature of covalent compounds. Which of the following is a correct name for CCl4? Remember that for these types of molecules, these covalent molecules, or covalent compounds, whatever element you have first, you just give it its name. If you only have one, remember that your prefixes are mono. If you're talking about 2, it's di. If you're talking about 3, it's tri. 4 is tetra. 5 is penta. 6 is hexa. 7 is hepta. 8 is octa. And so on. So the only exception for you using this is that when you are talking about the first element, so in this case it's carbon, and there's only one, you do not use the prefix mono. If you only had one of the second atom, then yes, you could use the term mono. But in this case, we're talking about the first element, so we would not call this monocarbon like they do in answer choice C. We would just say carbon. There's only one, but you don't use the mono for the first word in the name of the covalent compound. Secondly, you have 4 chlorides. So remember, this is 1, 2, 3, this is 4, so you would call it tetrachloride. So my answer would be A. For number 3, you're just ranking electronegativity. Please make sure that you memorize the values for electronegativity of your periodic table. Hydrogen is 2.1, then lithium is 1, and then you increase by 0.5. So 1.5, 2, 2.5, 3, 3.5, and 4. And that's all you have to memorize. So here I just went ahead and assigned the values. So you have hydrogen is 2.1, and then fluorine would be a 4. So you have 4 minus 2.1, which gives you 1.9. Between boron and nitrogen, boron would be 2, nitrogen would be 3, so that would be a electronegativity difference of 1. Nitrogen again is over here, so again you go 1, 1.5, 2, 2.5, and 3. And then right there it's between nitrogen and oxygen, so you just increase by 0.5, so the difference between these two will be 0.5. Beryllium and hydrogen, so you have beryllium right here, it has 1.5, hydrogen has 2.1, so if you subtract those you get 0.6. And then between carbon and fluorine, carbon is here with a with an electronegativity of 2. Which one? Sorry, carbon. So that's an electronegativity of 2.5, and then I'm comparing it to fluorine, which is all the way over here, and I know that that's 4. So that difference would be 1.5 if I subtract 4 minus 2.5. So then from there I just have to rank them. They're asking from least to greatest, so I'll start with the lowest one, which is 0.5. So that would be NO. That narrows my answer choices it narrows it down to C and D. Then from there I would have 0.6, which is beryllium hydrogen bond. That still doesn't tell me what my answer is going to be. The third one will be between boron and nitrogen. That still doesn't narrow it down. And then now I'm stuck between boron and nitrogen. You have, after that, you have 1.5, which is carbon and fluorine, and then the last one with the greatest electronegativity difference is that hydrogen fluorine bond. So my answer is D for that one. For question number 4, it says rank lattice energy. Which of the following has the lowest lattice energy? This one we kind of did as a warm-up. We did as a warm-up. If you don't remember, please go back to the LCISD Canvas page and look for that. But remember, all you have to do is find the charges. So you have potassium and iodine. Each of them brings in a charge of 1, so it equals to 2. And then if you go down these, you assign their charges, all of them come out to a number charge or a density charge of 2. And so from there, you just have to use their sizes to break this down. What I told y'all to do is to list all of the metals on one side and then the non-metals on the other. You're talking about ionic compounds, so each of these is made up of a metal and a non-metal. So the only metals that you're dealing with are potassium and lithium, and that's it. It's asking you for the lowest lattice energy, and remember that the lattice energy is inversely proportional to size. So the bigger the size, the lower the lattice energy. So you're going to look for the compound that has the largest size. If we talk about potassium and lithium, potassium is here and lithium is here. Potassium has more energy levels around it, and therefore its size is larger. So I'm going to focus on one. So I'm going to focus on the one that has potassium as an answer, so I can cross C out because it's lithium. And now I'm stuck between iodine, chlorine, and bromine. So if I look at my periodic table, I have iodine, bromine, and chlorine. You can see that the one with the larger size is iodine because it's further down, and again, you have more energy levels as you go down. So my answer in this case is potassium iodide. I did number 5 in another video, so you can go look for that. So I'm just going to go on to number 6. Number 6 is asking which of the following salts has an incorrect structure. And I believe we also did something similar to this in a warm-up. But all you have to do is balance out their charges. We know that chlorine is in group 7, so it has a -1 charge. There's 2 of these, so its charge is -2. Calcium is in group 2, so its charge is +2. The +2 and the overall -2 charge cancel each other out, so this structure would be okay. Sodium is in group 1, so its charge will be +1. Iodine is in group 7, so its charge will be -1. They also cancel each other's charges out, so they have a correct structure. That is not our answer. Letter C, you have calcium in group 2, oxygen in group 6. This has a +2 charge. This has a -2 charge. They cancel each other's charges out. It's a neutral salt, so they're good. But if you look at magnesium, this one's in group 2, so it has a +2 charge. Bromine, however, is in group 7, so it has a -1 charge. So this one is the incorrect structure. The answer would be D for number 5. Sorry, for number 6. For number 7, it says you're looking at assigning formal charges. Then it's asking you which of the following compounds does not have unpaired electrons on the central atom. You just have to draw out their Lewis structures. For oxygen, I just put oxygen in the center, then hydrogen on either side. I bonded them because otherwise this would not be a compound. And then from there, the hydrogens cannot take any more electrons. They already have 2 each because they're attached to the single bond. And so oxygen is the only one that has 6 valence electrons, and so it needs 2 more lone pairs in order to have a total of 6 valence electrons. So if you draw them out, carbon wants 4 bonds. It has them right here. Each hydrogen wants 1 bond. They each have their bond. So this one does not have lone pairs, and that's going to be our answer. If you look at pH 3, each of the hydrogens has their bond that they always want, but phosphorus is actually in group 5, so it's going to want 2 extra electrons, which are going to be a lone pair as well. And then you have NH3 up here. Nitrogen again is in group 5, so it only has 3 hydrogens to share electrons with. That accounts for 1, 2, 3 of its valence electrons, so it needs a lone pair in order to account for the total 5. The one that would be the one without unpaired electrons would be this one right here. For number 8, it says draw the Lewis structure for ethylene C2H4. How many bonds exist between 2 carbons? So you have the carbons in the center and then hydrogens sticking out from each one of them. The hydrogens we know cannot take any more bonds. We need a bond between the 2 carbons to connect them, but we know that each carbon wants to contribute a total of 4 electrons. And if we didn't draw this double bond, then they'd only have 3 bonds and we'd be missing 2 electrons. So that's why we have a double bond there, and so we say that there's 2 bonds between the 2 carbons. For number 9, it asks which of the following is the correct Lewis structure for ethanol C2H2O. A is not our answer because this carbon, so this structure it is not the most ideal one because this carbon only has 3 electrons around it. It's only contributing 1 electron to each of these bonds, and so it only has 3 electrons when in reality it's able to contribute 4 because it's in group 4. So that's why this one would be incorrect. Letter C would be incorrect because it has 5, well, this specific carbon has 5 bonds around it. 1, 2, 3, 4, 5. But carbon only has 4 electrons to contribute to the bonds around it. And the same thing goes for this one. It has 5 bonds around it, but it's only able to contribute 4. So then my right answer is this one. All of these satisfy the octet rule, obviously with the exception of hydrogen. But the carbon has 8 electrons around it, so it satisfies the octet rule. So does this carbon, 2, 4, 6, 8. And then this oxygen, 2, 4, 6, and 8. And they contribute their correct number of valence electrons. Hydrogen contributes 1, carbon contributes 4, 3 here, 4 here for this carbon, 2, 3, 4, 5, 6, and then hydrogen contributes another one. So B is the right answer for number 9. For number 10, it says Lewis structures resonance. So here we're talking about resonance. It's asking which of the following compounds does not exhibit resonance. So you have CH4, which is this one. We already drew it before. And the only real way you could exhibit resonance is if you have lone pairs to move around into double bonds. So here we have a symmetrical structure. We don't have any double bonds or any lone pairs to move around. So this would be the one that does not exhibit resonance. If you draw O3 or ozone, then you would see that you have a double bond here. You can move this double bond over to this side, take this lone pair off. So that would be another correct way to draw this. Same thing here, you have a double bond. That double bond could be over here between this oxygen and nitrogen, or it could be over here between this oxygen and nitrogen, so it would have 3 resonance structures. You could just move these electrons in. And then for this one, for CO3, this double bond right here could go over to this side, or it could go over to this side. And so that it would also exhibit resonance. Number 11, octet exceptions. Incomplete octet radicals. Which of the following compounds is a radical? Remember that for something to be a radical, it's going to have 1 electron that is unpaired. So not a lone pair, but 1 electron that's by itself. It's not a lone pair, it's not part of a single bond. And to do that, you're going to have to count the valence electrons for each one. Nitrogen is in group 5, hydrogen is in group 1, but because there's 3 hydrogens, that's 3, so 5 plus 3 is 8. 8 is an even number, so that will not be a radical. And so you do that, you calculate valence electrons for each one, and then total. Whichever one gives you an odd number is going to be your radical. In this case, it was answer choice B. All of these other numbers are even. Number 12, more exceptions. What is the number of electrons around the central atom in xenon tetrafluoride? So you have fluorine, let's see, you have xenon right here, you have 4 fluorine, so you go ahead and make a bond between all of the fluorines and the xenon. I calculated my number of valence electrons here. Let's see, so xenon's able to contribute 8 total electrons around it, but these fluorines will not actually want a double bond anymore because they're already contributing all 7 of their valence electrons. And so instead we add 2 lone pairs here. So it's asking number of electrons around the central atom. Here you would have 2, 4, 6, 8, 10, and 12. So my answer choice is D. This is one that you might have had trouble with. It's asking which of the following molecular geometries is not associated with an expanded valence. So I want you to become very familiar and very comfortable with the geometries handout or reference sheet that I gave you. It's asking which one would not be associated with the expanded valence. So you have these structures right here. You have the trigonal pyramid, which was this one right here. You have the seesaw, which is this one right here. You have the linear, which is here. And then you have the octahedral, which is here. So for it to have an expanded valence, you would have to have more than 8 electrons around the central atom. And if you look at these, each of these bonds is equal to 2 electrons, and obviously each lone pair has 2 electrons. So if you look at this one, 2, 4, 6, 8, 10, 12 around the central atom. That would be 12 electrons around the central atom. So this one would fit the expanded octet. If you look here, you have 2, 4, 6, 8, 10. That's also more than 8, so that would be expanded. If you look here, you have 2, 4, 6, 8, 10. So that's more than 8 valence electrons. It would also be expanded. But if you look here, you have 2, 4, 6, and 8. So you have the full octet. It would not be associated with the expanded valence. So my answer would be this one right here, which is the trigonal pyramid. For question 14, it's asking about bond angles. It's asking which of the following has bond angles of 180 degrees. And so if we start with HO2, which is right here, oxygen is my central atom, and then I have oxygen over on this side and hydrogen here. I have a single bond between hydrogen and oxygen. This one has 2 lone pairs, this one has 3 lone pairs, and so remember that these are going to push down on this oxygen. For it to have an angle of 180 degrees, remember a full circle is 360 degrees, so 180 degrees you would need to have a straight line to have 180 degrees between the bond angles. So essentially you're looking for the one that has a linear structure. If you look at I3, it has a linear structure there. If you look at NH2, it's angular, just like water. If you look at O3, this one also has that lone pair that's going to push these atoms down. And so my answer is B. For number 15, it says, in which of the following are the bond angles most distorted by unbonded electron pairs? You're looking at NH3, which is here, it has 1 lone pair. You have O3, which is here, it has 1 lone pair around the central atom. You have SCl4, which is here. You have 1 lone pair around the central atom. So all of these up to now have only had 1 lone pair. However, H2O has two lone pairs, so the unbonded electron pairs are going to create the largest distortion in this molecule because there's two instead of just one lone pair around the central atom. So my answer would be H2O. For number 16, it says, for which of the following compounds is the electronic geometry not the same as a molecular geometry? And remember, what we look at here, what we compare are the electron regions versus just the regions where you have the actual atoms bonded. And so if you look at beryllium chloride, you have beryllium here and you have two chlorines around it. Each chlorine is willing to contribute 7 valence electrons. It has 6 in the form of lone pairs, so does this one. And this beryllium is in group 2, so it's only willing to contribute 2 electrons. This would be a linear structure as far as electronic geometry. The central atom does not have any lone pairs, so the number of electron regions are the same as the regions of bonded atoms, and therefore its molecular and electronic geometry would be the same. If we look at BH3, again, you don't have any lone pairs, so the number of electron regions are the same as the regions where you have atoms bonded, so electronic geometry would be the same as the molecular geometry. You have CH4, again, no lone pairs, so the number of electron regions is the same as the number of bonding regions, and so electronic geometry is the same as the molecular geometry. This one's a little hard to look at, but you have sulfur in the center and 4 fluorines. Each fluorine has its valence electrons, total of 7 because it's in group 7, but the sulfur is able to contribute a total of 6 valence electrons because it's in group 6. So each bond contributes 1, that's a total of 4, and so we need 1 lone pair. If you see this one, sulfur tetrafluoride is the only one that has a lone pair as opposed to these other ones. So it's the only ones whose electronic geometry is going to be different than the molecular geometry. For number 17, it says which of the following compounds has a molecular geometry that is different from the others. And so if you put beryllium chloride, we did the same one up here. This is a linear shape. If you do ozone, this one would have a lone pair up here at the top. And remember that when you have that lone pair, the lone pair pushes these other electron regions away because it repels them. And so instead of having a linear shape like this, it's actually going to be an angular shape. I3 would be a linear shape because it does have all of these lone pairs, but they stabilize each other out, and therefore it doesn't create the bending that this one would. And then CO2, you have these 2 double bonds, but you don't have any lone pairs here to kind of push those down, so this would also be linear. For this one, it says what is the molecular shape of IF4 minus ion. So for this one, you have iodine in the center, and then we need 1 fluorine on each side. And we know that each fluorine is in group 7, so it'll want to contribute only 1 electron to that bond, and then it'll want to hold on to its other electrons for itself. And so now we just have iodine, which is in group 7, but right now it's only contributing a total of 4 valence electrons. So it's missing a total of 3. And not only that, but this is an ion which has a negative charge. So not only are we missing 3 electrons, we have to add another one because this is an ion. So we're missing a total of 4. These fluorines cannot take any more electrons, so instead of doing any double bonds, we can just add them in as lone pairs. And so it's asking for the molecular shape. If you look at your reference sheet, anytime you have 4 bonds and 2 lone pairs, this is going to be a square planar structure. For number 19, it's asking which of the following is polar. So just from experience and from drawing these out, I can tell that this is going to be polar, but we can go through all 4 of them. So you have carbon tetrachloride, you're going to have carbon in the center, you can put your chlorines out on the sides, We know that each chlorine is going to contribute 7 valence electrons. They're already contributing 1 to each single bond, and so we're going to draw 6 around them. So this right here is going to be a tetrahedral. And at the top you're going to have a chlorine, sorry, not a tetrahedral. This is going to be, it will be a tetrahedral, but what I'm trying to say is that you will have one of these chlorines sticking up from the top, and these chlorines are going to be sticking out to the sides. But because it's the same atom all around, remember the symmetry part, this is going to be nonpolar. And we're looking for the polar one. So this would not be our answer. CH4, you have the same thing. It's also going to be a tetrahedral. You have 4 hydrogens. Again, same atom all around, so this would be nonpolar. And then you have CO2, which we drew up here, so I won't have to draw that again. You have carbon, you have 2 oxygens, they are double bonded, and each of them has 2 lone pairs. The carbon, however, does not have any lone pairs, so this would not be polar. It's the same on both sides, the same atom with the same number of lone pairs, and so this is symmetrical. This would not be polar. The only one is this one right here, CH3Cl. You have carbon and you have 3 hydrogens on the sides, but then you have 1 chlorine at the top. And because this atom is different than the rest, this would be considered a polar molecule. So again, just try to look for the ones that have the same atoms on the outside. Those will be your nonpolar ones. If you have a tetrahedral that has 1 atom being different, then that's going to be your polar molecule. And then lastly, for question number 20, it's asking which of the following is not polar. So you have ClF3, which I drew here. You have chlorine in the center, and then you have the 3 fluorines outside. So each of the fluorines wants to contribute 7 valence electrons. You give it 3 lone pairs, gives you a total of 6 electrons, and then it contributes 1 to the single bond. So that makes all the fluorines happy. Now you have chlorine in the center, which is in group 7, and so it's contributing 3 electrons here, 1, 2, and 3, and so you give it 2 lone pairs, 1, 2, 3, 4, to get a total of 7 valence electrons. The octet rule is satisfied for each of these, and it is a polar molecule because it has these 2 electrons here. Remember, whenever you have this type of shape, you have your 3 atoms bonded to the central atom, and then the 2 lone pairs, you would get this T shape over here. And so because those electrons are not opposite of each other, and because you don't have like a 4th fluorine here to kind of even everything out, this would be a polar molecule. If you look at SF4, you have sulfur in the center, and then you have the 4 fluorines around. If this were just the fluorines around the sulfur, this would be a nonpolar molecule. However, sulfur is in group 6, and right now it's just contributing 4 bonds, so it has to find a way to contribute those 2 extra electrons, and so that'll be in the form of a lone pair. Again, you're not going to have something to balance this lone pair out, and so this will be a polar molecule. For IF4-, iodine is supposed to contribute a total of 7 valence electrons. Right now it has 1, 2, 3, 4, and I misread this. So you have a plus sign, which means that we lost an electron. So the fluorines are happy. They're each contributing their 7 electrons in the form of 3 lone pairs and 1 bond to these shared bonds. But iodine is supposed to have 7, and instead of worrying about it having 7 valence electrons around it, we can take that plus sign and just assign that charge to iodine. We can assume that it's the one that's going to lose the electrons, so we have 1, 2, 3, 4, 5, and 6 instead of 7. We give it this lone pair, which is what makes iodine, or not iodine, but the whole molecule polar, because there's no other lone pair to balance this out. Before I talk about xenon F4, I had a question today in class about, so the way that I explain this is if you have this lone pair, there's no other lone pair to balance it out. well, I had a question. Someone asked me, how come these two don't balance each other out? So we talk about that T shape, and the T shape is actually a polar molecule. The reason for that is that these two lone pairs are not actually exactly opposite of each other, and because of that, they don't cancel each other out. So instead, they create kind of like an angle, and that creates the polarity. Now, when you look at something like xenon F4, you have xenon in the center, and then you have the 4 fluorines on the outside. We made them happy. Each of them has a full octet. They're contributing their 7 valence electrons. But then you have xenon in the center. It's supposed to contribute a total of 8 valence electrons because it is a noble gas. And so, based on these bonds, you just have 4 electrons that it's contributing, so you need 4 more. So you would give it 2 lone pairs. Now, the geometry that this creates is a square planar geometry. And the reason that this becomes square planar, I'm trying to see how I could draw this. So maybe you could show this one sticking out to the back, this one sticking out to the front, this one sticking out to the back as well, and this one sticking out to the front. So the reason that we have this square planar geometry and not kind of like that pyramid shape that we get from the trigonal pyramid is because you have that pair of electrons sticking out to the top. And then the other pair of electrons is actually down here at the bottom. And so this would be a nonpolar molecule because these atoms that are attached around xenon are all the same atom. They're all fluorine. And then in the center you have the electron pair at the top and the electron pair at the bottom, which cancel each other's pulls on the electrons out. So this would be my nonpolar molecule.